Okay, so for this chapter that we're going to go over, we've kind of picked and selected a couple sections from this. We're going to talk about some matrices and kind of the basics of matrices. The first thing that we're going to talk about today is just how you can perform operations with matrices, which means like adding them, subtracting them, multiplying by a scalar, and just kind of doing some of the real basic operations. We're not going to do anything super fancy today. When you think of a matrix, okay, it's going to be this kind of set of numbers that are going to be in rows and columns, and they've got like these brackets that kind of sit around them. And so what we're going to see is anything that looks like these three here. When you're looking at a matrix and you're trying to decide its dimensions, you always look at the number of rows that it has, and then the number of columns. So rows would be the numbers that go from left to right, and columns would be the numbers that go up and down. So for example, for matrix A, so normally matrices are notated with like a capital letter. So capital letter A, we've got two rows, because we have the 1, 2, and the 3, 4s, the two separate rows, and then we also have two columns. So we would write that as a 2 by 2 matrix. For B, how many rows do you guys see? There's more than that. How many rows are in row B, or in matrix B? Rows are what go across? 3. And how many columns are there? 1. So B would be a 3 by 1 matrix. So how do you guys think we would name C? Good. 3 by 3. 3 rows, 3 columns. Now that'll come in more handy when we're dealing with actually multiplying matrices, but we're not going to do that for a couple of sections now. What we're going to do with multiplication today is just multiplying by a scalar. What a scalar is like, it's like a scale factor, so it causes something to either increase or decrease in size. If it's a whole number, or if it's a number greater than 1, so if it's 1.5, 2, 2.5, 3, so on, it can cause something to become bigger, where if it's between 0 and 1, so if it's a half, a third, a fourth, those would be things that are going to kind of decrease the size. Think about like photography. When people take pictures, they can either blow something up or they can reduce it down, like to wallet sizes. So that's using a scale factor to either increase it or decrease the size. So when we multiply by a scalar into a matrix, what you're basically doing is thinking of the distributive property. You're going to take that number that's out front of the matrix and you're going to multiply in to all of the numbers inside the matrix. So for this one, we're going to take 2 times all of those numbers inside there. So 2 times 1 would be 2. 2 times 0 would be 0. And then we do 2 times negative 2 and 2 times the 3. So we get negative 4, 6 on the bottom. So I want you guys to try the second one there. Multiply all of those things by a half, and it's okay if you get decimals. Okay, so check yours and make sure that you got the same numbers I did there. All right, let's go to the next page here. So if we have something that are considered to be equal matrices, that means that the matrices have the same order. So that means that they have the same rows, the same columns, and the same corresponding positions are equal. So that means that like the top left corner on both matrices is the same number or the same letter. And all of the other terms or all the other positions in the matrix also match. So they basically have to look identical. They have to have all the same numbers, all the same number of rows, all the same number of columns. Now, if they give us two matrices and there's an equal sign in the middle of them, we can assume then that that means that they are equal. And we can use that to solve for missing variables inside of another matrix. So for example, this first one, I'm told that these two matrices are equal because there's that equal sign in the middle. That means that like the x minus 3 and the 1 should equal each other. The 3y and the 12 should equal each other. And the z and the 3 should equal each other. So those places should correspond to one another because they're in the same spot as the matrix of the matrices. So when I set them equal, I should be able to either just know what the variable equals or I should be able to solve for it pretty easily. So for example, for the x, I would set x minus 3 equal to 1. And then to solve for x, I would just add 3 to get 4. So there would be the value of x. Now for y, we're going to do 3y equals 12. So then I would divide by 3. And I get 4. And then z is kind of already going to be given to us straight out. So z equals 3. That's just going to be my answer there. And then if you look at that last place that I didn't highlight, they both say 6. There's no variable there for me to find. But that just, again, it follows it and lets me know that those matrices are equal to each other because those pieces match. Okay, so I want you guys to take a look at the second one there. I'm going to help you guys get this one started only because that first matrix does have a 2 sitting out front. So the first thing that you're going to want to do on the second one is actually distribute that 2 in here first. And be really careful with like the y plus 1 and the z minus 3.5. Make sure that you distribute to both of those terms. So it's almost like I'm having to take 2 times 3 separate times on the top and on the bottom. So now it's going to say 2x and then 2y plus 2 on the top of that new matrix. What's the bottom going to say? Good. Okay, and now that's equal to that other matrix, the 16, 12, 3z, x plus y. Okay, so now you guys take a minute or two and try to finish solving this. So set up your equations. You may have to solve for certain ones first before you can solve for the one that's got multiple variables in it. Okay, so I got 8 for x, y is 5, and z I got 10. Now the last one, you don't really have to solve it, but you could use it if you just wanted to check and make sure that you did everything right. So like that last one has a couple of variables. It has the z, and it has the x and the y. So really what I could do is take those values that I found for x, y, and z, plug them in, and just make sure that it still makes that matrix equal. So in for z, I'm going to put 10. So I have 2 times 10 minus 7. And then in for x, we put 8, and in for y, we put 5. So 2 times 10 would be 20. 20 minus 7 would be 13. And 8 plus 5 is also 13, so it does check out, which just lets me know that this is an equal matrix, and I did find the right numbers for x, y, and z. Now if we look at this third one, if we look at both of them, no matter how you set this up, you're going to have more than one variable given to you in both equations. So when I set 2x equal to that 16 minus 3y, and when I set 4y minus 14 equal to x, both of these equations have the x and the y value. What I'm going to do is use substitution to help me solve for one of the variables first, so that I can then go back and solve for the other one. So substitution, remember, means that you take one of the equations and you solve it for one of the variables. Now this one already has that done for me. On the left-hand side, x right here is all by itself. It just says x. X is equal to that same quantity, 4y minus 14. So what I'm going to do is actually take this piece, 4y minus 14, and in this equation over here, I'm going to put that in for the x. So this is that substitution method. We talked about this a couple chapters ago. So I'm going to put in that 4y minus 14 in for the x. So there's a 2 out front. So I'm going to put that 4y minus 14 in parentheses right next to the 2. And then that's still going to say equals 16 minus 3y. I'm going to distribute the 2. So we have 8y minus 28 equals 16 minus 3y. Now I only have one variable. I just have y's. So I'm going to finish by solving for y and then using my y value to go back and help me solve for x. So in this one, I'm going to combine like terms. So what I would do is add 3y to 8y. That's going to give me 11y. And then add 28 to 16. That's going to be 44. And then I would divide by 11. So y is going to equal 4. So then what I can do is take my y value and come back to either equation. It really doesn't matter which one. I do think that using the one on the right is going to be a little bit easier, just because I won't have to worry about that 2 that's attached to the x in the first equation. So I'm going to plug it into the second one here. I'm going to take 4 times 4, because that's what I found for y, minus 14, and that's going to be my x. So that's going to be 16 minus 14, so x is going to come out to be 2. And if you really wanted to, you could always go back up to your original matrix. You could plug in the x and the y value on both of them and just make sure that they do equal, and they should. Okay, so we're going to continue talking about these matrices. What we're going to do now to kind of end it is add and subtract them together. Now the key here to adding and subtracting matrices is that they have to have the same dimensions. So they have to have the same number of rows and the same number of columns. If they don't, so if they have different dimensions, we can't add or subtract them because you wouldn't have something for everything to pair up with. So they all have to have the same rows and same columns so that when I go to add and subtract, all of my terms have something to match up with. So on this first one here, if I look, I have, for both of them, I have 2 rows and I have 3 columns. So these are both 2 by 3 matrices. That means that I should be able to add them or subtract them. Now this one wants me to add. And when you add, you just take the terms that are in the same position in the matrix and you add their numbers together. So for this one, the 1 and the 2, you add those together, and so that's going to give us 3. Then I would do the same thing with the top. So the 3 in the middle and the -4 in the middle on the second matrix. 3 plus -4 is going to be -1. And then the last numbers in that top row, 0 and 3, we add those together, and we get 3. Okay, you guys do the bottom. What did you guys get for the bottom row of numbers here? Good. 2, 0, and then 5. And that's all there is to that. Number 2, can we add those? Or subtract them, I should say. Why not? Right, they don't have the same dimensions. This first one has 2 rows and 2 columns, so it's a 2 by 2. But the second one has 2 rows, but it has 3 columns. So if I were to try to subtract these, I would be pretty good for all of these numbers, and then that 8 -4 gets kind of left in the dust, and I can't really have that happen. So this one's not possible. So if you're not able to do it, you just need to say not possible. Okay, or another way to say that would be like it's undefined. It's not able to be found. All right, so now what we're going to do is combine what I've talked to you guys about. So for these ones, we've got scalar, so we're going to multiply first into the matrices, and then we're going to either add or subtract them. So for this one, that first matrix, we're going to multiply everything by a 2. So it says 2, 0, 6, 16, -8, and -2. For the second matrix, you're going to multiply everything by 5. So we have 5, -5, 0, -10, 15, and 20. And I'm adding these matrices together. So 2 plus 5 is 7. 0 plus -5 is -5. And we're just going to keep adding those matching terms together inside of this matrix. So I got 7, -5, 6, 6, 7, 18. So I'm going to let you guys try number 2. Be really careful with those minus signs. Okay, because that's where I see mistakes happen the most, is if you try to go through this too fast, you're going to end up adding when you should be subtracting, or vice versa. So be really careful with those negative signs, but go ahead and give it a try. So what I did, and you could do something different and still get the same answer. When I multiplied, I just took positive 3 and positive 2 and multiplied that into these matrices so that I left the minus sign out front. Now, if you took the negative 3 and the negative 2 into the matrices, then that causes you to have to add them because you're removing the negative from in front of the matrix, and so that it becomes a plus sign. So then, if you did it that way, your signs might look a little bit different than mine, only because it would have shifted into the matrix. So, like your second two matrices, you should still have the same numbers as me, but they should all be opposite signs. So it should be like negative 12, negative 18, positive 15, positive 3, 0, negative 3, and so on. Then you end up adding yours. Now for me, because I just took the positive, I still subtracted. So I did 1 minus 12 minus 2 to get negative 13. At the very end, you guys should still get these same numbers. So if you didn't get those same numbers, I would just go back, check your signs. Like I said, subtraction ones are the ones where I see the most mistakes because we forget to either pull the negative in, or if we use the positive, we forget to subtract. So just be really careful with those ones with the minus signs. There's one more here that I've got on this page. We're going back to having something with letters here, and we're trying to solve for the values of the variables. And this is similar to what we saw on the previous page, but it's a little bit different because I'm not just setting the quantities equal to each other from one matrix to the other matrix. I'm going to still have to distribute this 2 on that first matrix. So now it's going to say 2x and 6. And then we still have minus 1, 4 equals 7y. At this point, I'm just going to set up the two equations that I see with the subtraction sign and the equal sign in the middle. So I'm going to write 2x minus 1 equals 7. And then for the other one, we're going to do 6 minus 4 equals y. So that one's pretty easy. Y is just going to be 2. For the x, I'm going to add 1, so I get 2x equals 8. And then I'm going to divide by 2, and I get x equals 4. So it's not any more complicated than what we were doing on the previous page. It just looks a little bit different because you have to use like a scalar and then add or subtract.